notion, the standard paradigm of black holes that has been around for a long time. And so that's what we now want to do. So first of all, what is the, maybe I should give you the references for this part, which is going to be following. So the references for this part, we're beginning today. So basically there are 2 or 3 lectures now. There is a review article, which is in Living Reviews. So it is, or is it in archives, is GRQC 04.07.042. And basically here you need sections 1 to 3 and 5.3. And there's also another review article, other review article, and that is by Booth in GRQC 05. I don't think this article, although it came a year later, has anything more than the previous article, but it presents it from new angles, so it might be useful. And then from the notes that you have on the web page, and they're not complete, that's why I'm giving you this. From notes, you could also look at on the web. Yeah, it is chapter 5. So this is the material. This is the last part of the black holes that we will be doing. This is the material. Okay. So what is the standard paradigm then? Then the standard paradigm has been this paradigm, as I said last time, was kind of laid down by Hawking, Carter, and many other people in the early 70s, and that has been used very much. The first is, of course, the notion of event horizon. And this is the boundary of the past of Scribulus. This is the event horizon that we saw. So you need asymptotic flatness. You look at all of past of Scribulus and you look at its boundary, and that boundary is null, and is always null. So this is the result, it's a null. This is the causal past. And then that is the event horizon. And then in the stationary case, the equilibrium situations. The standard paradigm is that the equilibrium situation is represented by the space-time with a Killing vector field, so stationary space-time. So in addition to the event horizon, the whole space-time. So this is the entire space-time. So this is a global. Globally, we have got a Killing vector field. Not just in the neighborhood of the horizon, but everywhere in space-time, there is a Killing vector field, dA, which is a time translation at infinity. Near infinity, space-time looks like Minkowski space-time. Therefore, we know what we mean by time translation. And so this is the standard paradigm. And then usually people have just done basically, in most work, as I said last time, focuses on, used to focus on stationary black holes. plus linear perturbations. So you take Einstein's equation, you linearize them, and just the first order fluctuations, if you like, is what one is looking at. So linear perturbations of the stationary black holes. So this has been the standard paradigm up here. So the point up here is that if you have got a killing vector field, the killing vector field is, if you move the diffeomorphism that is generated by the killing vector field, it's an isometry. It by definition preserves the metric. That's what it is. The event horizons are an invariant construct. In other words, I give a space-time, and you see, is there an event horizon? And if there is, then you locate it, and then you could choose some coordinate system, you could choose some conformal completion and find the event horizon, and you could choose another coordinate system, another conformal completion, find the event horizon. It was the same event horizon, because you only use the intrinsic property. You have not used any additional structure in the construction of the event horizon. So if the asymptotic flatness of space-time does not depend on extra structure, and the causal structure of space-time is just given to you, and therefore event horizons are really invariant notions. Which means that if I have a motion in space-time which preserves the metric, then it must preserve the event horizon. It's a trivial statement, but it's a powerful statement. So you can use it just not for event horizon, but for any invariantly defined submanifolds in space-time. That if in fact the manifold is invariantly defined, then it is a fact that every isometry must leave it invariant. Why? Because I move along the isometry, the metric hasn't changed. The metric has never, doesn't feel any experience. And all this is constructed just from the intrinsic properties of the metric, therefore this object doesn't change at all. So just the general result is that, general result of fact is that every killing vector field in the space-time is tangential to the event horizon. You also saw another invariantly defined notion, which is null infinity. If you figure a space-time, you attach to a null boundary, and therefore it is also a fact that if you have got a killing vector field in the asymptotically flat space-time, then it extends to the null boundary, and it's always tangential to it. So these are just general facts for the fact that which come from the simple property that the killing vector field, diffeomorphisms along killing vector field doesn't change the metric, and therefore if you have scry and you make up a diffeomorphism, the metric is the same. So for the image metric, is the same. Therefore for the image metric, scry is the same, and therefore this vector field cannot move scry, cannot be away from scry, and therefore it must be tangential to scry. So this is also true for scry. And in fact, using this fact that all killing vector fields must be tangential to scry, and furthermore must preserve the invariant structure of scry, which we'll describe in the second part of the course up here on vibration radiation. This can be used to classify the kind of isometries, the kind of killing vector fields any asymptotically flat space-time can have. Because if it's a killing vector field, it must be tangential to scry, and there is some intrinsic structure on scry that it must leave invariant. So you say, what can it be? And then you can classify, and you can show how many killing vector fields an asymptotically flat space-time can have. The answer is at most 4, and 3 rotations and a time translation. And if in fact the asymptotically flat space-time has a time translation, there is no radiation at all. So if there is radiation, and it cannot be spherical symmetric either, and therefore if there is radiation, it can have only one killing vector field, and that must be a rotation. All these things just follow from general considerations, and that is why I'm emphasizing this as a side remark. Coming back to the black hole space-time, the killing vector fields are all tangential to the event horizon. So for the Schwarzschild space-time, we saw that non-rotating black holes, I got 4 killing vector fields. which are time translation, and the 3 rotations. Right? And this is null. This is time like at infinity always, and it's null on the horizon, the event horizon, and these are space-like on the event horizon. For the curved space-time, we got these 2 killing vector fields. Of course, these are 4 independent killing vector fields. Any constant linear combination of these killing vector fields is also a killing vector field. But when you say 4, I mean the group is 4-dimensional. So TA, we got 2 killing vector fields. So group is 2-dimensional. This is translation time. Again, it is time like at infinity, and we got only 1 rotation. This is again space like at infinity, but a surprising thing was that this time like killing vector field is also space like at infinity, is space like at on the event horizon. It's time like at infinity, but on the event horizon it's space like, and it becomes null on the ergo region, at the ergo sphere, and then in the ergo region it is space like, and in particular the event horizon, which lies in the ergo region, it is actually space-like. But what we can do is we can just consider a vector field, let me call it Ka, to be equal to Ta, and then the horizon, the angular velocity of the horizon, omega h times phi a. This is just Ta minus t dot phi upon phi dot phi. Evaluate the horizon, that's angular velocity, times phi a. We can just consider this vector field. Now since this is evaluated the horizon, this is actually constant. We wrote down last time a formula for it in terms of the radius of the horizon. So therefore this is just a constant. So therefore this is a constant, this is important. And I am taking a constant linear combination of the 2 killing vector fields. Therefore this is also a killing vector field. And your homework problem is really looking at this vector field. I think we call it alpha A because I did not restrict it to the horizon. We just define alpha A to be equal to Ta minus t dot phi times phi dot phi times phi A. So Ka is just the restriction of alpha A in your homework to the horizon, just on the horizon itself. And the statement is that in the space-time this is a function, but on the horizon the function happens to be constant, and therefore I get actually a constant linear combination of 2 killing vector fields, and I can look at this constant linear combination everywhere. So away from the horizon, K is different from alpha A because this is a function in alpha A, whereas this I'm keeping constant. So I get a particular killing vector field, and this killing vector field is null. This is a null generator, or this is null at the horizon. I'd emphasize that in Schwarzschild spacetime we got a T, in curved spacetime we got T and alpha, and the 2 roles are kind of split. So T is a time translation at infinity, T is a time translation at infinity. But T became null on the horizon, whereas alpha becomes null on the horizon, or if you like, this K becomes null on the horizon. These rows split up here. Okay. So this is a perfectly fine killing vector field, but this is not a time translation because this is a constant times rotation. See, the time translation is norm remains 1 as you go to infinity. This is 1. It's limited. This is finite. It doesn't grow. Whereas the rotation is just d by d phi vector field. So its norm goes like r squared. If you like, in the Cartesian coordinates in Minkowski spacetime, phi a looks like x times y hat a minus y times x hat a, where x hat and y hat are unit vectors, and x and y go to infinity at spatial infinity. Therefore, the norm blows up linearly in R at spatial infinity. Therefore, at infinity, this is what dominates. Therefore, the killing vector field, which is null on the curved horizon, is actually space-like at infinity. So these roles are, whereas the killing vector field, which is time-like at infinity, time translation at infinity, is space-like on the event horizon. Okay, so that they are different from each other. But nonetheless, what we see up here is that in both cases, this is the main point, they represent black holes in equilibrium. So hence, and the killing horizons, the event horizon is a killing horizon. With respect to the killing vector field K. In other words, Ka, a killing horizon, as we saw several lectures ago, it's a three-dimensional surface which is null, such that its null normal is a killing vector field. So it's proportional to killing vector field. And therefore here we've got a killing horizon in both those cases. So this is why the literature, or when people give talks, depending on what talk it is, right? They would say horizon. They might mean really a killing horizon. Right? When they talk about Rindler horizon, etc., it's just a killing horizon. It is nothing to, not an event horizon at all. Sometimes they do mean event horizon. Now, event horizons don't have to be killing horizons. So, if the black hole is not in equilibrium, event horizon is not killing horizon. If a black hole in space-time is not in equilibrium, then in general, of course, there will be no killing vector field at all in space-time, and therefore, the black hole horizon is not really a killing horizon. There is no global killing vector field at all. So this is the standard paradigm, namely the equilibrium black holes. Black holes are characterized by event horizons. In equilibrium, they are stationary, and then in the stationary black holes in equilibrium, we actually have uniqueness theorem, so therefore it is really the Kerr family. I write Schwarzschild separately because it has qualitatively different global properties. 4 killing vector fields, only 2 killing vector fields. But in both cases, the event horizon is a killing horizon. Okay, so this is the standard paradigm. Any questions about this? Everything clear so far? Yeah. Okay, good. So now, the next part of the course, part 7, is limitations. I shouldn't really call it standard paradigms because these limitations have been understood for almost 2 decades, but still people continue to use this kind of paradigm. As I explained last time, I quoted Martin Rees as saying that they often say that everything was really done in the 70s, and after that it's all engineering. And I think now what we are going to see is that this is not quite the case. That in fact there were open questions, many of them have been answered, and in fact the paradigm we need is somewhat different from this paradigm that we studied. It doesn't mean this is not important. It is important. A lot of things can be done with just Kerr black holes and perturbations thereof, but in the fully nonlinear regime, and black holes are dynamical, this is not sufficient. So that's what we're going to do. So the limitations of this thing. So let me just go in the order. The first limitation is really that this notion is too global. Notion of event horizon. Now what do we mean too global in this? Well, too global for what? Well, too global for being useful in practice. So what does the notion of event horizon say? Well, it says, give me the full space-time, right, to infinity. And then I'll put the null boundary, see if it's asymptotically flat. If it is, then I put the null boundary. And then I look at the past of this null boundary. But in numerical simulations and so on, people don't have 2 black holes, right? They are constructing a space-time which represents 2 black holes. So the practical problem will be construct I say 2 black holes because people are studying, for example, black hole collisions, black hole mergers. So you want to know how they merge, when they merge, what happens, how much radiation is emitted, and can LIGO detector see it or can they not see it? This is what we want to calculate. Well, but here, with the event horizon notion, I really don't know how to start, right? Because what this means is that I start with two black holes, I evolve them, they're going around each other, intuitively we know what all this means, but I don't know if they are black holes until I have the whole space-time. But what am I trying to do? I'm trying to solve numerically the whole space-time. So I don't have the whole space-time, right? That is my goal. So really you can talk about the black hole after the numerical simulation is done. But numerical simulation of what? Because how can I say what is a black hole, right? So I think everybody's smiling, so I think everybody understands that is the problem. So namely, so the question here is what is a black hole? Initial data, for example. And event horizons are not very useful for this because I need the whole space-time. Event horizon is not useful. So of course you must say, wait a minute, but what did numerical people do? So of course they did not use event horizon, they used something else. And so this is what we're going to do. What they need is a quasi-local notion of a black hole, right? Which doesn't depend on where it is scrying. Such thing, just given the data, I can look and see if there is actually what I would like to call a black hole in this initial data. And so we need that, and event horizon doesn't do that. If once you got the whole space-time, you can evolve back and see where the event horizon was, and then it's all okay. But during evolution itself, we cannot really use that notion very much. So the other thing is the following, right? This is a more conceptual point, but I think it's important, right? Why is there an event? Say, look at just the spherical collapse of a star, right? So simple spherical collapse of a star, and so therefore the picture is so the question I was asking is why is there an event horizon? How does it arise to begin with? Well, the event horizon, as you can see, is clearly tied to the existence of the singularity. So for example, if I have a spherical collapse of a star, then if I just have, then what happens is that this star collapses. This is RT plane, this is time running this way. So star, and this is the world tube of the star. So this is the world, this is the ball, this is, so to say, this ball represents the star at an instant of time, and it collapses, it forms a singularity, and as we saw last time, then I got an event horizon here for me, which is hiding the singularity from infinity, right, from square plus. But supposing I had a star which collapsed. It collapsed a little bit, and then for some reason, for example, some quantum mechanical force, we know this happens for neutron stars, for example. So I could have actually a star collapsing and then forming a neutron star. There's no singularity there. And then neutron stars, say, continues to exist forever, just isolated neutron stars. Then how would the Penrose diagram look like? Well, again, it's a conformal picture. Therefore, only light cones are always at 45 degrees. But spatial distances are distorted. Here, for example, the star looks larger, here it looks smaller, but in fact, even the distant past, it was not smaller. This is just the artifact of our conformal factor that we used to conformally compactify space-time. Physically, the star radius is just like that and just monotonically decreasing. So don't look at this and say, oh, the star was small radius here and large radius here. This picture portrays the causal structure completely faithfully, but not spatial or temporal distances. So therefore, what happens in a star? So this star again is just sitting there, maybe collapses. So again, here you cannot see it. Collapses, forms a neutron star, say, and then the neutron star just stays. So in this picture, again, it's going to look like that. And therefore, because of confound factor omega is going to 0 at the end, so that it looks like that. So therefore, and then sky just looks like that, sky plus, sky minus, and this is again our star. So in this case, past of sky plus is all of space-time. There's no black hole here, right? In this. But now suppose I got a star which collapses. In this case, neutron star, we all understand. What prevents it is the Fermi. Those of you who don't know, quantum mechanically, you cannot put two fermions in the same state. Therefore, effectively, if you try to do that, there is a repulsion, and that repulsion is called the Fermi non-degeneracy pressure. So, if you try to contract two neutrons too much, you cannot do it, because you have so many neutrons, they are fermions, and they have to occupy a certain amount of space, and therefore the statement is that the star is finite. But if a neutron star has mass bigger than, say, 5 solar masses, then the gravitational pull cannot counterbalance the Fermi attraction, and then in general relativity, coupled with this quantum matter, we know that in fact black hole will form in that case. But this is all in classical general relativity. Supposing, in fact, when the black hole is all formed and it reaches a Planck density, as I think we saw, Planck density is about 10 to the 94 grams per cubic centimeter. The nuclear density is about 10 to the 14 or 10 to the 15 grams per centimeter. The Planck density is 80 orders of magnitude higher than the nuclear density, which really is completely astronomical. It's not easy to imagine these things. But there can be new physics there. In particular, there can be quantum gravity. And supposing there is actually also quantum gravity, some repulsive force, which actually stabilizes star at the Planck scale. So singularity does not form. Everything is regular. Then the picture would look like that and not like that. So by changing general relativity at Planck scale, you can make event horizons disappear. Again, this is a strong statement, so I just want to say, it is true that by changing general relativity at very high densities of matter, I mean, I said Planck scale just because that's what we mean by physics. That's the physical scale that we have, but mathematically you just choose a scale at which you modify Einstein's equations and say that something else happens then. Einstein's equation is not valid in that region where the densities and the curvatures are so large, then the event horizons can disappear. And this surprisingly was to me it was surprising, that was pointed out very early on by Abhay Ashtekar. Isaac actually is how it's pronounced, but Peter Isaac, Isaac, and this is a PRD 36, 65, 1987. So these are way before anything about loop quantum gravity saying that there are such repulsive forces and such thing. He pointed out, I mean, of course, his modification of ad hoc. And I just quote from his abstract. He says, space-time structure is manipulated at the Planck size in a neighborhood of the singularity. This modification can remove the event horizon completely. However, Hawking radiation still survives. That was the main thing that he wanted to say. So the statement is that event horizon is so global that modifications at the Planck scale inside the star can make the event horizon disappear. Right? So somehow this is not quite right. Why is it not quite right? Because in this region the star is well in its Schwarzschild radius. So this is just a spherical collapse. This is what spherical collapse of the star. So it is well within the Schwarzschild radius, right? So outside, if I look at what is happening to the light cones and so on, all the light is being focused, and so if I'm here somewhere within the Schwarzschild radius, then whether I'm here within the Schwarzschild radius or whether I'm here, I'm going to say locally, I'm going to say the same physics, and yet the event horizon says, oh no, here there's a black hole, but here there is no black hole, and somehow you would like to say that, well, this is too drastic a notion, that somehow I should be able to accommodate. I should be able to say that, well, no. If the star has really shrunk down below the Schwarzschild radius, then the physics outside the star would be very similar to what is happening up here, as if, because in fact local geometry is exactly the same, right? It's 1 minus, or you can write down the metric to be equal to -1 minus 2m over r, dv squared plus 2 dv dr plus r squared. And that metric looks exactly the same here as it looks here. Here, just outside of here. And yet, in this case, we said, no, there's no black hole. And so this is kind of a limitation up here. I hope you're a bit shocked, because this is shocking. I mean, that there are such blatant limitations which are not never, but almost never discussed, right? I mean, none of the books will says this, for example, right, explicitly. Okay. And the second is related, but logically distinct, is the fact that the notion of event horizon is teleological. That is to say, I cannot say if there is an event horizon in this room right now. It may be forming, and in fact growing in this room. Literally true. I'll just show you in a minute. Okay. Literally true. I don't know. Why? Because it may be that 100 million years from today, there's a gravitational collapse in the center of the galaxy, and then if I drew the event horizon back from there, it will be passing through this room. And I don't feel anything in this room. Right? So we'll see in a second now. Indeed, with the notion of event horizons can form and grow in flat regions of space-time, in Minkowski space. They can do that. So again, you say, wait a minute, this is ridiculous, right? I mean, in this room, there's no event horizon. I should be able to tell. My notion should be that. So they would say, yes, this region is a black hole region. I mean, wait a minute, if this is a black hole region, I should be able to do some local measurement. Maybe not instantaneous measurement. Maybe I have to wait for a year. Maybe I have to take over 1 million years. But I should be able to do some measurements here, not infinite time, and being able to say that, well, is there a black hole or is there not a black hole? I hope you agree with these sentiments. So the second thing is, B, is that event horizon, the teleological conclusion. And this is something that it can be most directly brought out by a simple example. This example is the following. This example is a gravitational collapse, but it is a gravitational collapse not of a star, but of a null fluid. And it is so trivial, technically trivial, that you can do it in 5 minutes on the board. So let's just do it. So you just write down the metric to be equal to what looks like the Schwarzschild metric in the V, in the retarded coordinate, in the advanced coordinate that we have written down several times, namely dA squared equal to minus dV minus 2 more R dV squared plus 2 dVdr plus R squared d over v squared. This is the advanced Eddington-Finkelstein coordinates. We use this, for example, to understand the Kerr geometry. We have to understand the ring structure of the Kerr singularity and so on. But what we now do is that m in Schwarzschild is a constant, but now you make it a function of v only. So it's changing in time. The mass is actually changing in time. It's not fixed, but it's actually changing in time. And the picture that is happening up here is the following, that I got scry. And what we're doing is, we're throwing in some radiation. So instead of making a black hole by collapsing a star, we're making a black hole by throwing in some radiation. You can think of the electromagnetic waves if you like, but which is modeled out of a null fluid, which I'll write down what that null fluid means. So there's some null fluid which is forming into the black hole. Okay. So there is some null fluid up here. I'm just sending in null fluid. Which is falling into the black hole up here. And then, if you do that, then what happens is that in fact, singularity is formed. So the structure actually looks like this. So this is scrap plus, this is scrap minus. I mean, this looks smaller than this. That's just my drawing. I could have drawn better because the scales are, again, conformally, lengths and so on don't matter. Conformally, diagrams up here. and then I got an event horizon. So I'm going to explain this diagram in a minute. So this is again R equal to 0 in our space-time. And I'm throwing in some null radiation up here. So, and then I get a singularity that is formed up here. And so this is a singularity, and this is the event horizon. So let's draw the event horizon up here. This is the event horizon up here. This is null fluid, so this null fluid has stress energy tensor, which is proportional to grad AV, grad BV. These are null vectors. These were our Ka, Kv in the Schwarzschild metric, in the Kershel form that we looked at. And then we got a coefficient, and the coefficient is just equal to m dot of V upon 4 pi r squared. So, this is spherically symmetric space-time. But it's not static. It's time dependent because there's no global killing vector field. It's time dependent because V is the retarded instant of time, and this depends on. You just choose. You specify a function. A function m which depends on time function of time. Instead of being a constant, you make it a function of time. And then, surprisingly, this actually is a solution to Einstein's equations, namely Einstein tensor. Of course, given any metric, you can just write down this equation and declare what is on the right-hand side to be the stress energy tensor. But here the point is that the stress energy tensor has a direct physical meaning. Namely, you are saying that in this case, I got here m of v equal to 0 if v is less than v naught. So this was v less than this v naught. So therefore, in this region of space-time, right, in this region of space-time, which is going to be in yellow, the metric is just flat. Because here m dot of v is 0, right? So v is running this way. This is the v coordinate. So here m of v is 0, and therefore m dot of v is 0. And therefore in this region we just have metric which is Minkowski metric. So m of v is 0, therefore we just get Minkowski metric is just minus dv squared plus etc. So in this region m of v is equal to 0. So we get Minkowski space-time. It's a flat metric, right? It's completely flat metric up here. And then the null fluid starts coming. As a null fluid comes in, of course, space-time acquires curvature. So now the space-time has acquired curvature, and in this shaded region, space-time is time dependent. So there is no killing vector field. In this region, of course, I got 10 killing vector fields because Minkowski space, the whole Poincare, the infinitesimal 10-dimensional Poincare transformations can act up here. So this is Minkowski space. I mean, the key point is that all of these are Minkowski space. Up to here, when the m of v starts, for v less than v naught, so this is our v less than v naught line. This is our v less than v naught line. To the past of this blue line, this is a patch of Minkowski space-time. Then here, the radiation stops, so m of v is also 0 here. Sorry, m dot of v is also 0 here, there's no more radiation. But m of v now, see m dot was non-zero here, m of v has accumulated. So here, this is v equal to v1. And so in this region, I got a mass m of v equal to say m1, which is m of v1. Right? Because m dot is non-zero, so it's accumulating. Therefore, value of n here is whatever it is. And after that, the value of m of v doesn't change. And then again, this is a constant, so it is a Schwarzschild metric. So in this region up here, what I have is a Schwarzschild metric. In this region, we just have a Schwarzschild. So basically, I got a sandwich between the Minkowski spacetime and the Schwarzschild spacetime. And the sandwich, what is causing the sandwich is radiation, null fluid, which is going in up here. So we draw the event horizon. I look at Scri plus, I look at sparse. I get this. Well, this event horizon is a striking feature. It is forming in Minkowski space, and it's growing. This radius is increasing as you go up here. And so the event horizons can form and grow in Minkowski space-time. Why? How did it happen? How did it know that I should be an event horizon and I should be growing up here? How does it know? It knows because it anticipates that, say, 1 billion years later, there is going to be a gravitational collapse. And then, in that space-time, if you look at the event horizon, if you look at the Scri and draw the causal past and go back in time, you'll find that there is an event horizon. So they are teleological and there are two global in the sense that we'll just explain here. And that this is kind of the limitations of the notion of event horizon, and what we would like to do is to overcome that. Are there any questions? So this is one of the shortest part of the course, which is number 7 for black holes, namely that the notions of event horizons, or the notion of the standard paradigm has limitation. The third limitation, and then we go on, is the following. The third limitation is that black hole in equilibrium is described by a globally stationary spacetime. So this means that the entire space-time is time independent. You like, if a black hole is in equilibrium, right, then what you like is that in the geometry of the black hole, whatever is like the horizon or something, geometry of the surface of the black hole is time independent, it does not change in time. This is the thing that we want. But here we ask that it be the entire space-time be time independent, be stationary. Now, of course, this is an idealization that we often make in physics, but in this case, I think there is a limitation. Why is there a limitation? This is something we're going to see in a few minutes, in a few lectures, but at the moment, I think most of you have heard about this miraculous black hole thermodynamics, and entropy is related to area, etc., etc. So let me just assume that you have heard about that. And what one does is, one assumes that everything is really globally stationary and proves some laws, which are called laws of black hole mechanics. And then one sees that there is a great similarity between those laws and laws of thermodynamics. And this really is one of the deepest things that has come out of general relativity, because it's general relativity, it's purely general relativity is being used, but it suggests that there's a connection to thermodynamics, and when you put together, then it suggests that there's a connection to quantum mechanics. So this laws of black hole mechanics is a pillar which brings together general relativity, thermodynamics, or statistical mechanics, and quantum mechanics. And that's why it's considered very deep. But when I do, for example, ordinary thermodynamics, supposing there is some fluid up here, and I want to do, talk about thermodynamics of this fluid. So I say, in equilibrium, the temperature of this fluid is constant. Then I say, if in fact heat this fluid a little bit, do something to this fluid a little bit. It was in equilibrium before, it again comes back to equilibrium. Then I got the first law. We're going to see this in some detail. I got the first law of thermodynamics, which says that delta E, change in the energy of this fluid, is given by temperature T times change in entropy delta S. So delta E is equal to T delta S plus work done on this fluid. But when you do this, we say that this little fluid is in equilibrium. This is time independent, this is stationary. It doesn't say the whole world is stationary. Right? These laws don't say require that the whole world should be stationary. They don't say that, well, there should be nothing else in space-time except for this fluid. I mean, it's a statement about a system. Here also, we're talking about these laws of black hole mechanics. That should be a statement about the system and should not assume anything global. So in particular, laws of black hole mechanics which are supposed to be close to thermodynamics. Should assume only that the black hole is in equilibrium. So there is some stationarity or something like for the black hole, but not for the whole space-time. So these are the three limitations. The notion of event horizon is too global and teleological, and when we talk about equilibrium states, we should not really be talking about stationary space-time, but somehow black hole itself is in equilibrium in some suitable sense, and can we do that? And that is the part, that is the point of the next part, which is to say overcoming these limitations. And so this limitation is overcome by the notion of quasi-local horizons. And this particular part is longish. It's just like curve was longish. It will have several subparts up here. So now what we're going to do is to see how these three limitations can be overcome. But are there any questions about this? Okay, good. So quasi-local horizon. So the idea is, as we just saw, the idea is really that we should be able to say if in fact something is, so something about black holes using just geometry in some region. In this, I look at this room and I should be able to say that there is a black hole or there is no black hole, right? So that is the idea. And so the first part up here is really looking at the notion of marginally trapped surfaces. So how would we say that there's something interesting happening in space-time? For example, this picture that I had drawn up here. I should be able to say something interesting is happening up here when the mass m is the mass has fallen inside the Schwarzschild radius, right? So if in fact I am outside the Schwarzschild radius and outside r equal to 2m and all the mass is inside, then I should be able to say something interesting happened here. So what is that is happening? And what happens there locally is what we call the marginally trapped surfaces. So this is what we're now going to see. Okay. So what is the idea? So go back to Minkowski space. So flat space-time. And consider a two-sphere. So let's suppose this two-sphere is r equal to constant and t equal to constant. So I use some Minkowskian coordinates r, t, theta, phi, and then I say r equal to constant and theta, t equal to constant. So this is a two-sphere which is coordinatized by theta, phi. So it's a two-sphere up here. So this is two-sphere. And I look at light fronts. So I've done that before. There is outgoing light front. This is outgoing light front, which is called LA. And LA is equal to, I'll put hat now not to mean any confound completion because we don't have any confound completion, but just to mean unit vector. So there's a unit radial vector R hat plus D hat A. And it is, some people just define it like that, often fine, but sometimes one puts the square root of 2 up here for normalization reasons that will become clear in a minute. And then there is another. So this is perpendicular because it's in the radial and time directions, both these vectors, and this two sphere is only the theta phi direction. So this is normal to this two sphere, two surface, so let's call it two surface S. And then the other normal to the two surface, NA, is going to be the inward one. So it's going inside. So this is NA. As I was saying before, I mean, you think of this two sphere at the instant of time, and I just instantaneously light it. Then the light front will travel outward. That is going along LA, and then the light front will also travel inward, and that is going along NA up here. So outgoing is LA. The area here is increasing, and the area here is decreasing. So NA is just equal to theta minus R hat A upon square root of 2. Therefore, LA NA equal to -1, and the square root of 2 is just to make it -1 rather than -2. So I got this outgoing and incoming rays up here. And what we can see is, we can calculate what is called the expansion. So basically, this light front is expanding. So for example, if I just focused on the outgoing one up here, then light front here was something at one instant of time. Time is always running that way. And this is the light front at another instant of time. So this is at time t1, future instant of time. And this light front is expanded. So this sphere has bigger radius than this sphere. And this is captured by calculating what is known as the expansion. So if you calculate the expansion, so what we do is we are going to look at the metric to be equal to GAB. And I'm writing down the full Minkowski metric, or eta AB, if you like in this case. The Minkowski metric eta AB to be equal to minus D hat A, D hat B, plus R hat A, R hat B. So this is the metric in the TR plane. And then I got the metric which you normally write as R squared D omega squared, and I'm just going to call it SAB. This is the two-sphere metric, or if you like R squared. Let's just call it SAB. This is the two-sphere metric. Its radius of this two-sphere metric would be R, so it would be R squared times unit two-sphere metric. So what we do is the following. We just take this derivative of LA, grad A and B, I take this derivative, and I project it along the two sphere. So it's like the extrinsic curvature, if you like, but for a lower dimensional subset. This is a simple way of doing it in mathematics literature, but in physics literature, what we do is we just take these two sphere, and then we look at one of them. There are two null normals, or two normals to the two sphere, and we are taking is how is the normal changing, and then we project it back into the two sphere. So I just put here SLC. So I just project it back. So this is the derivative, how the normal changes, and we project it back and see how it. So it's like the one of the extrinsic curvatures, if you like, of the two-dimensional manifold. So this object, this object has two parts. First part is a trace part. So this is a second rank tensor. Second rank tensor field on the two sphere S2 that I got. So we can divide it into two parts, trace-free part and the trace part. So that's what we do. So we just write this as trace-free part the space bar. This is symmetric. Second rank tensor field which is symmetric. You can check easily if I take, excuse me, so let me leave this as an exercise. Show that this is actually symmetric. If I take a skew symmetrization here, substitute up here, you will see that it's actually 0, just because each of them is a gradient. Right? T is a gradient, T hat is a gradient, and R hat is a gradient. So this is symmetric. So trace-free part plus trace. And this trace-free part is called sigma AB, and the trace is called theta. Okay. So this is called shear, and this is called expansion. This is elementary geometry. So expansion, let me write here explicitly L here. It's shear of L because we're taking the L normal, and therefore expansion of L is just given by SAB times graph A. And the shear is trace-free part. So sigma AB of L is equal to take SAC, SAB, and remove the trace. So there's the trace-free part, and there's a trace. So there's a shear, and there's an expansion. Now the expansion really is what you think it is. Namely, it is telling you how this area of these two spheres is changing. And I'll leave this as an exercise for you to check that this is actually positive. So that really comes from the, I should write this just T hat A plus R hat. So that just comes from the fact that I got a plus sign up here. See, grade L. L is going to have T hat and R hat. But grade is just, this is Minkowski space time, so you can take d by dt, d by dx, d by dy, d by dz. Therefore, grade TB is just 0, so what matters is just grade R up here. And R is just a unit radial vector. And the statement is that in one case, I get plus grade R, in the other case, I'm going to get minus grade R. So this is positive here. And then for the other non-normal, it is negative, and that just comes from the sign up here. So you can check that. Might be in your homework problem is to check that explicitly. So we get here, so this is called the expansion. So expansion here is positive for here because the two-sphere light front is expanding. Here the expansion is negative because the light front is contracting. That is what is happening. It's not very profound. That's it. What about shear? Shear is what it sort of seems like, right? So it has nothing to do with the expansion itself. You might have a null congruence, for example, null congruence which just looks like that. So this is not a causal diagram. So in time, the null congruence just looks like that. So it's not expanding at all. But it may be shearing. So the cross-section area remains the same, but it's actually shearing. If that is happening, then theta would be 0, but sigma would not be equal to 0. Okay, so these are the two things that are happening. Now in Minkowski space, we just see this is the case. And in Minkowski space, you can draw any two sphere. And we'll always have one of the expansion, let's call theta sub L, will be positive, and theta sub L. So any two sphere. It doesn't have to be R equal to, I would choose a very simple one, R equal to R0, T equal to T0. I can take two sphere like that. And again, calculate the expansion. There's going to be one normal for which expansion will be positive, and the other normal for which expansion is negative. Now what happens when there is a gravitational collapse? Well, when there is a gravitational collapse, we have seen some time ago that light cones, so to say, tip in space-time. So in fact, if I had a light gravitational collapse like that, a star up here, this is a star, it collapses, pops a black hole. This is not a causal diagram, so this does not mean it's a time-like line. It's just a coordinate pictures up here. So this is really just R equal to constant line up here. So there's a singularity, and then the statement is that we got a event horizon that forms, and the event horizon will look like that. And then we looked at the null cones. Out at infinity, null cones are at 45 degrees, looking like that. This is not causal diagram. In a conformed picture, null cones always look at 45 degrees. This is just a coordinate picture, RT plane, so to say. And then as we come up here, closer to the, up here it always looks like that. But as I come up here, then they start tipping. And over here, as we saw, they actually tip so that the future, so they look like, so they start tipping. So all the entire future directed light cone is, all the future directed light rays are going inside up here. So this is a trapped region. So what is happening up here is, and then inside the event horizon, as we saw in the case of the black hole, inside the event horizon, both the outgoing and incoming ones are falling into the singularity. They are not expanding. They are not going out to infinity. They are falling into singularity. So what is happening is, what distinguishes Minkowski space from this is, or the black hole region, is that in Minkowski space, the expansion of the light rays going out is always positive, and the expansion of the other light rays is always negative. That is what is distinct. So we would like to say that a marginally trapped surface is one on which one of the expansions, say theta, so right? I mean, L and N are just names. So we just say one of the null normals, L, its expansion is equal to 0, and the other one is negative. So instead of these light rays going out, expanding out, if the expansion is 0, that means the area is not changing. That means the light front is frozen. So that is what happens on the horizon. Light front is frozen. That is what happens on the horizon up here. Light front is just frozen. Here, the light front is just frozen. It's just frozen. This is R equal to 2n, and therefore 2m1, and therefore the mass of the Schwarzschild black hole is m1, and therefore it's the R equal to 2m, m1 surface up here. And here the radius is not changing at all. Therefore the expansion is 0. And the other expansion going inward is negative as usual. And a trapped surface is a two-sphere on which this is true everywhere, and the trapped surface is one on which both expansions are negative. So light actually not only is not going out, but cannot even stay put. It has to converge inside. No matter which light ray you look at, it's always converging inside. So this is a region in which light is trapped, of course instantaneously, right? If something is happening, if this is satisfied at the instant of time, then instantaneously the light ray is all going inward. If this is happening instantaneously, then what we're saying is that the light ray instantaneously, the outward going light front is frozen, and the inward one is contracting. So this is the notion of marginal trapped surface, and this is what we want to use very strongly in the notion of quasi-local horizons. So again, as we just saw in Minkowski space, no matter which two surfaces you choose, one of the expansion will be positive, the other will be negative. Therefore, this can never be satisfied. So there are no trapped surfaces or marginally trapped surfaces in Minkowski space. So in this room, there are no trapped surfaces. I mean, you wait for some time and see if this is the world tube of this room. There are no trapped surfaces. One light front will be outgoing, the other light ray will be incoming, and they just tame Minkowski type geometry. And we would like to say that yes, in this room, then, if you wait for a billion years, nothing profound happens, then in fact this is still, there's no black hole anywhere. So the idea up here is to use this notion of trapped surface and marginal trapped surface to define quasi-local horizons. So this is the key idea. Please ask me, and it's a very simple idea, it's not very profound, but ask me if there are any questions. Yeah?
So in general relativity itself, all marginally trapped surfaces will be event horizons, but not...
No. No. No, we will
there's
see
no
that.
one-to-one relation, like there's no...
For example, at some point I just erased it. There are, so I should not remember. I got this star which is collapsing, and it goes to Planck density, a very small radius. So R is equal to 2m, says it's a solar mass star. So So 2m is about 3 kilometers for our sun. Supposing the star actually collapses to a centimeter size, which is about moon. Moon short radius will be about a centimeter, and then it stops. It doesn't go anymore. Then the statement, but still the mass is the mass of the sun, not the moon mass. Then if I'm just outside here, there is a trapped surface. So I can say something is happening here because something is trapped surface, but there's no event horizon in this. So the difference is, maybe I should try. This is a good question, and I should try now. What is the difference between having trapped surfaces and marginally trapped surface and event horizons? So unfortunately, I'll do that. Okay, so here is the situation in which, again, the picture doesn't do justice, but I'm telling you that this solar mass star collapses, goes to lunar mass, and then just stays at lunar mass up here. In this picture, because I go to infinity, because of confound factor, this looks like it's shrinking, but it really is constant. Anything which is constant because the factor of omega going to 0 will look like it is shrinking. And then I got square plus here and square minus here. So out here, it is indeed the case that the light is going to be, I got a marginally trapped surface up here. But the point is that if I wait long enough, then light will still go out to infinity. Whereas if a black hole were to form, so having marginally trapped surface just means instantaneously the light front is frozen. Okay? Instantaneous light front is frozen. Whereas here it means that in fact this will be the event horizon up here. Instantaneously the light front is frozen, but I will never get out of infinity. Whereas here, I mean, this is really the past of this region up here. So we can draw the full global diagram, and you can see that you wait long enough, there are light rays which will escape out to infinity, but the statement is that it is not. I just calculate what is the expansion up here, and I will find that I can find at r equal to 2m, I will find that the expansion actually here locally is 0. Or in this case up here, maybe I should draw this diagram. Now, I'm running ahead of myself, but in this case, if I look at this picture, right? If I look at this picture up here, where we got the event horizon right here. We got the event horizon right up here. But if I look at the surface, I can also look at surfaces at which r is equal to m of v. Now, in this region, there is no m is 0, so that just r equal to 0, so I don't get anything. But once I get in this region, when the starts, then in fact, this is non-trivial surface. So this surface, r equal to 2m, this surface would look like this. So it starts at r equal to 0, then it grows. Once the matter starts falling, it grows. I'm sorry, this is wrong. It keeps growing. I mean, this picture doesn't show faithfully that it's growing, but r is actually increasing from 0 to m1. Here now r is equal to 2m1. And then it's 2m1. So in this region, the marginally trapped surface would be the event horizon. But in this region, it is not. So that's the point of view. So what is happening is that, okay, let's just leave it at that. We'll come back after we're done. So there are marginally trapped surfaces, but the statement is that those marginally trapped surfaces mean that instantaneously light would not escape. What happens in the largest, if you wait long enough, what happens? Yes. Now, if in fact energy conditions are satisfied in general relativity, then all the marginally trapped surfaces are inside the event horizon. And therefore, what we are saying will be true, that in that case, I should not erase it. What we said is true, that in that case, the statement is, it's not marginal trapped surface is not necessarily part of the event horizon. Marginal trapped surface is not part of the event horizon, but it's inside the event horizon. Okay. So you're saying, is it part of is it event horizon? No, but is it inside the event horizon in general? So in general, if energy conditions are satisfied, then it is inside the event horizon. And the picture, which I should not have erased, I erased up here. There, of course, I was bringing in new physics, say from quantum gravity, which did not have any, was not general relativity. And when that happens, this theorem, which says that marginally trapped surfaces are always inside the event horizon, fails. That's not true. So that's what I was just meaning there by saying that in that case, this theorem fails, and therefore for a while, nothing will come out of, instantaneously light rays don't escape, but in fact, I don't have any event horizon, yet I have marginally trapped surface in that case. Okay. So this is, at some level, extremely elementary. At some level, it is very difficult. It is very difficult for people who know a lot about black hole physics, but don't know this subject up here, because it involves a lot of unlearning. Right? Anytime you have to unlearn, it is always difficult, extremely difficult. Learning is much easier than unlearn, as you probably know, unlearning, right? That's why quantum mechanics is difficult, right? If in fact we never learned about classical mechanics, and we just told quantum mechanics was the way that the world is from the beginning, it would be easier. But we have to unlearn classical mechanics, things that we are prejudiced about, and so on. Similarly here, we have to unlearn a few things about, what our intuition is about, in order to do this. Okay, so just to summarize, I pointed out three limitations of the standard paradigm, and then we're just begun talking about how to overcome it, and the main tool that we're going to have is really to use the notion of these marginally trapped surfaces. And a quasi-local horizon is just a world tube of marginally trapped surfaces. So I got one marginally trapped surface, another marginally trapped surface, another marginally trapped surface. We just stack them. So here, each of these r equal to 2m of v is a factor. I'm not showing it. Is a fact, is a marginally trapped surface, and therefore this world tube is what is going to be replacing this event horizon. And why is it a reasonable thing to do, and what has advantages and limitations is what we're going to see. So we're still going to have at least 2 more lectures on this, and then we'll be done with the black holes. Okay.